Hello students, let's go to next topic about syllabus. If you remember, in last period we have seen coefficient of emission or emissivity. Now afterward, today we have to see the Kirchoffs law of heat radiations. So Kirchhoff has created one law which related to the how much heat get radiated by the body, that was explained by the Kirchoff in his law. What exactly the statement of Kirchoff's law? Kirchoff's law in short we can say the coefficient of absorption of the body is equal to coefficient of emission of the body. Coefficient of absorption of the body equal to coefficient of emission of the body, or another way we can say another statement, the amount of the ratio of emissive power of body at the ratio of emissive power of body to coefficient of absorption is always constant, and that constant is equal to emissive power of perfectly black body, and that can be represented as, or mathematically we can represent as, the R divided by A equal to RB. The ratio of emissive power of the body to the absorption coefficient of that same body at the same temperature is equal to emissive power of perfectly black body. This is one of the statement of this Kirchoff's law, and this is alternative statement, or we can say the coefficient of absorption equal to coefficient of emission. Why so? Because we know in this equation we can write this as R divided by RB equal to A. Just move this RB here, A to this side. So we get this R by RE nothing but E. So E equal to A or A equal to E. So this is a mathematical relation that will give the Kirchoff's law of radiations of the white body, which can say that at given temperature ratio of emissive power of the body to the coefficient of absorption of body is always equal to constant, and that constant is nothing but a emissive power of perfectly black body, or another way coefficient of absorption is equal to coefficient of emission. Now we have to prove this. To prove this, there is one experiment here. That experiment is said to be thought experiment. So thought experiment is the experiment. By using this experiment, we are going to prove this Kirchoff's law. So what is the thought experiment that we have to see? So thought experiment is nothing but one of the experiment which shows that when suppose we have some enclosure, suppose one enclosure we have taken. In this enclosure, two bodies we have taken. So this is the first body and this is second body. Both of them have same surface area. Everything is same. Only difference is what? One is the ordinary body. This is the black body. So this is the perfectly black body. So we can say this is the black body and this is the ordinary body. Ordinary body and the black body. So these are the two bodies we have taken. So ordinary body and perfectly black body that we have taken. These two bodies are there. Both bodies are kept in same enclosure such that temperature of surrounding is same in both the cases. Temperature of surrounding is same in both the cases. Suppose both of them have some area, so same surface area A, and let us consider everything is same. So after some time, this ordinary body absorb the radiant energy incident on it. At the same time, it will emit also. Same case would be there for black body. Whatever the radiation incident on it, it will absorb. At the same time, it will emit the radiations. So suppose Q amount of radiant heat incident on both the bodies. Q amount of radiant heat incident on both the bodies. Now here we have to derive this equation, derive this Kirchoff's law. Suppose total Q amount of radiant heat incident on ordinary body and black body. First of all, we will derive the equation for ordinary body. Same equation we will derive for the black body. Then we will divide both equation and then we will get the required proof of Kirchoff's law. So let's start with the first. So when radiant energy incident on body, ordinary body is Q, and suppose out of this Q, QA amount of heat get absorbed by this ordinary body. QA amount of heat is absorbed by the body, and absorption coefficient of this is A. So we can write the total radiant energy absorbed is A into QA, quantity of radiant heat absorbed. So we can write one equation at equilibrium here. Amount of heat absorbed by the body must be equal to amount of heat emitted by the body. So I will write that equation here. Amount of heat absorbed by the body. Suppose this is body A and this is body B, black body. So amount of heat absorbed by body A must be equal to amount of heat radiated or emitted by the body A. So they must be same. Amount of heat absorbed must be equal to amount of heat emitted. So how much amount of heat it get absorbed? It is nothing but just we have seen out of Q, QA get absorbed, absorption coefficient A. So we can write A into QA equal to amount of heat radiated is what? It depends on radiating power, or okay, power radiated. Suppose power radiated in ordinary body it is R, and black body it is R suffix B. So here it must be equal to R. That is equation 1 for ordinary body. Similarly, same equation if we apply for black body, what would be the equation? The equation becomes Q equal to RB. That is equation 2. Now the question come in your mind that here we have taken A for ordinary body. For black body, why we have not taken A? Because in case of perfectly black body, whatever with the radiation incident on it, everything get absorbed by black body. So A equal to 1. So we can write 1 into Q, or simply Q equal to RB. So that is why we have not taken A here. Now what is the next step? Next step is what? Divide equation 1 by 2. So just divide equation 1 divide by 2. So what we get? Divide equation 1 by 2. For example, suppose QA is nothing but the amount of heat absorbed. So instead of Q, suppose out of Q amount of heat get absorbed depending on absorption coefficient. So you should not show here A, you should not show here A. Otherwise this Q can't get cancelled out. Let's go further. So divide equation 1 by 2. What we get? Divide this by this. So we can write here AQ divided by Q equal to R divided by RB. So here what we have done? Divide equation 1 by 2. By doing that, we get this equation. Now this Q from this side cancelled out. What we get? A equal to R divided by RB. But we know the power radiated by ordinary body to the power radiated by perfectly black body, that is nothing but the emissivity or emissive power, that was represented by E. So we can write A equal to E. So this is the required proof we have done. Or we can modify this as we want this proof. If you want this proof, we get it here. Okay. If you want this proof, R by A equal to RB, rearrange. Move this R here, RB here. Hence, we have proved the Kirchoffs law of radiation. So, power radiated by the body must be equal to power emitted by the body. Power absorbed by the body equal to power radiated by the body. By that equation, we have used a thought experiment in which in single enclosure we have taken two bodies, body A as an ordinary body, body B as a perfectly black body. If Q amount of heat incident on both the body, then we know that at normal temperature, all bodies absorb the heat radiation as well as at the same time they will emit the heat radiations. By that concept, we have written one equation, A into Q equal to R for ordinary body and Q equal to RB for black body. Divide these two equations, solve it, we get A equal to E, coefficient of absorption equal to emissivity. That is nothing but a required proof of Kirchoffs law. Now let's go to next topic of syllabus. That is nothing but a spectral distribution of black body radiations. When black body emit radiation, how the radiation get distributed along the spectrum of black body, that we have to see. So spectral distribution of black body radiations. So in this situation, what we have to learn here, when temperature of body is more, it will radiate more energy. If temperature is less, it will radiate less energy. Same thing here. There are two scientists whose name is what? Lummer and Prichim. Lummer and Prichim. Lummer and Prichim. These are two scientists who have studied the distribution of energy, radiant energy, in case of perfectly black body with respect to wavelength. So for that, this is the energy distribution curve he has drawn. Energy distribution curve, power radiated or radiant power, radiated or emitted by the perfectly black body with a wavelength along x-axis, power radiated along y-axis. So this graph gives the distribution, spectral distribution of power radiated or radiant energy emitted by the black body. From this conclusion we have to draw. So before going to conclusion, let's see what exactly it is. As wavelength increases to right hand side, here if you see the first curve, it is 300 Kelvin I have taken. Temperature of the body is 300, not, it's not 300, 3000 Kelvin. 3000 Kelvin temperature we have taken. So what will occur with the radiant power? It increases, become maximum with increase in wavelength. For further increase in wavelength, it decreases to minimum value, or we come to the zero, we can say. Same, if we increase the temperature 3000 to 4000 Kelvin, same, radiated power, it increases to maximum value as wavelength increases. At certain wavelength, it is maximum, and further it is seen that it decreases. Further increase in wavelength, it becomes decreases. Same thing occur for 5000 and 5500. But here there is a most important parameter to learn is what? The wavelength for which the power radiated is maximum, that wavelength represented by lambda max. So see, first case, here it is. The power radiated is maximum for this wavelength, so it is said to be lambda max for 3000. For 4000, I have drawn dotted line. This is lambda max. 5000, this is lambda max. 5500, this is lambda max. From all this diagram, it is seen that this maximum wavelength for which power radiated is maximum, this one, and this one. It is seen that they are shifting toward the origin. The wavelength for which the power radiated is maximum is shifted toward the origin, and that is nothing but what? One of the law that is said to be Weins displacement law, that we'll see in the next topic. So that one point I have to told you. Apart from this, area under the curve represent how much power is radiated by the body. Suppose 3000 degrees. So this is the graph, we can say. This is the area under this curve below 3000 Kelvin. So within this part, whatever be the area this much, this area under this curve gives the power radiated by this body at 3000 degrees Celsius. If we go to 4000 degrees Celsius, if you see, this is the area under the curve. So this area under the curve is nothing but what? Power radiated by body at 4000 Kelvin. So we can say as temperature increases, area under curve get increase, means power radiated increases. So it says that as temperature increases, body radiate more power. At 5500, it will last, the first one, this one, it has maximum area among all because it has maximum temperature. That is nothing but it will radiate more energy at 5500 Kelvin. Now let's start with some conclusion. So this is the graph we have learned. From this graph we have to draw some conclusion as they have given in a book. So let's start with the first. At given temperature, energy is not uniformly distributed. At given temperature, energy is not uniformly distributed in the spectrum as a function of wavelength of black body. See, as this temperature 3000, suppose, energy is not constantly distributed. It increases to certain maximum wavelength, maximum value, certain wavelength, lambda max, then again decreases. So there is not a continuous distribution. It distributed non-uniformly. It is not uniformly distributed. That is the meaning of the first conclusion. Second, at given temperature, radiant power emitted initially increases with the increase in wavelength, reaches its maximum and then decreases. The wavelength corresponding to radiation of maximum intensity lambda max is the characteristic temperature of radiating body. That already we have learned. As here the wavelength increases, the energy radiated increases. It becomes maximum for certain wavelength, and that wavelength is said to be lambda max. That is characteristic at this temperature. Then further increase, wavelength increases, energy radiated decreases. That is nothing but this conclusion. Here point to remember is what? The maximum wavelength emitted by object. Remember, it is not maximum wavelength emitted. It is a wavelength for which maximum radiant power is emitted. It is just, we have given the name as lambda max, but it is not maximum wavelength. It is a wavelength for which maximum power is radiated by the black body. That is point to be remembered. Next one, area under curve represent total energy emitted per unit time, per unit area. Area under curve, this is black part, this is part, this we have seen. So the area under curve represent how much energy is emitted by the body per unit area, per unit time. That was given by area under curve. The next one, the peak of the curve shift toward the left. Peak of the curve, just see the peak, top is here initially, here it shifted, here it shifted, here it shifted. So it is shifted to left side toward the origin, means toward the shorter wavelength or larger frequency. It gets shifted. So see the fourth one, peak of the curve shift toward the left or shorter wavelength. That is the value of lambda max decreases with increase in temperature. Yes, here lambda max for 3000 is here, 4000 is here, 5000 is here, 5500 is here. Means what? The for as temperature increases, lambda max shifted to the origin or it decreases, we can say. That is the fourth one. Fifth, at higher temperature, the radiant or total energy emitted per unit time or per unit area, that is area under curve, correspond to all wavelength. Yes, it's common sense. See, if you consider this part, first curve, if you consider, it start here, it ends here. It will contain this much wavelengths only. Okay, if you go to last one, so this 5500, it will have start here and it will end somewhere here, suppose. So this much wavelength it will consider. So initially it has small wavelength range. Now for higher temperature, it will cover a maximum wavelength. So it will correspond to all wavelength, we can say. That is nothing but this topic. Then next one they have shown at temperature 300 Kelvin. 300 Kelvin means the room temperature. It is seen that there is a most intense wave which has a wavelength of 5 into 10 raised to minus 6 meter. 5 into 10 raised to power minus 6 meter, which is smaller, different from the value. Practically all radiant energy at this temperature carried by the wave longer than this wavelengths. This is the most intense, other than the long remainings are much more weaker than this. So this is nothing but what conclusion we have drawn from this black body radiation spectrum. This is said to black body radiation spectrum sometime. So in most of the examination up till now, what they have done, they have asked the same question on the board examination. Draw the spectral distribution of black body radiations. So you have to draw this curve properly with this wavelength, radiant power, temperature, you should mention lambda max and so on. Draw the peak properly. If draw was asked the question, you have to draw the diagram. Second type of question they will ask, draw the energy distribution curve of perfectly black body radiation and give the properties from the curve, or explain the properties or characteristic from the curve. So that you have to explain. As change increases, the temperature increases, what will occur? Lambda max shifted to this side, the first thing. Second, lambda max is nothing but what? The wavelength at which the more power radiated by the body. That's second thing, and so on. That 4 points we have seen, that 4 to 5 point you have to mention here. So this type of questions will be mostly asked in board examination. Now let's go to next, Wien's displacement law. So what exactly this Wien's displacement law is related to this? Wien's displacement law is related to same diagram. So let's start Wien's displacement law. So as it is a Wien's displacement law, so there must be displacement. Displacement of what? As temperature increases, lambda max displaced to this side, shifted to this side, and that is said to be Wien's displacement law, which says that the maximum, the wavelength for which radiant power emitted is maximum is found to be direct inversely proportional to temperature. Inversely proportional to temperature. So we can write lambda max is inversely proportional to temperature. Lambda max is a wavelength for which radiated power is maximum is found to be inversely proportional to temperature. Temperature increases, just see here, temperature increases, lambda max decreases. Same thing. So that is displacement in the wavelength with temperature, and that is said to be Wien's displacement law. If we remove the proportionality sign, we can write here as lambda max equal to B divided by T, where B is said to be Wien's displacement constant or Wien's constant, whose value is 2.897 into 10 raised to minus 3 meter into Kelvin. And here apart from this, you can just rewrite again this, move this T to this side. You can write lambda max into T equal to B, that is nothing but a constant. So this is nothing but a Wien's displacement law. Where this type of law is used, this type of law is used to find out temperature of distant star, sun and moon. Different stars are in our galaxy. We can find the temperature of different star by using this Wien's displacement law. Apart from this, they have mentioned one term here, white dwarf and red giants. White dwarf are nothing but stars. Basically, they are star whose temperature is about 10,000 degree Kelvin. That much high temperature stars are there. They find to be white in color. And apart from this, red giants are nothing but what? The another thing which are little bit cooler. Their temperature is less than this white dwarf. And the temperature of red giant is 3000 Kelvin. So that is the difference they have just mentioned. Apart from this, let's go to next topic of the syllabus, and there is a probably last topic of this chapter, and that is nothing but what? Stefan's law, sometimes said to be Stefans and Boltzmann's law. Now remember, Stefan's law or Stefans and Boltzmann law that we have to learn here. So let's start with the Stefan and Boltzmann law. Stefan Boltzmann law. Stefan and Boltzmann law, and it is again related to radiations. So it is law of radiation. So what exactly this law says? Initially, there is one scientist whose name is Stefan. He says that the power radiated by perfectly black body is directly proportional to fourth power of temperature, and this law, again same law, was proved after by Boltzmann by using the laws of thermodynamics. That's why combinedly Stefan has created as well as Boltzmann have proved the same law. That's why it is said to be Stefan Boltzmann law of radiation, which says that rate of emission of radiant energy per unit area per unit time, or power radiated by perfectly black body per unit time per unit area, is found to be directly proportional to fourth power of temperature. So power radiated is represented by R. It is directly proportional to T to the power 4, and this is said to be Stefan Boltzmann's law. That much this much simple this law is. Now here we can remove this proportionality sign again. You can write this as equality sigma into T to the power 4, R equal to R is sigma is a constant of proportionality. It is said to be Stefan constants. Its value again they have given 5.67 and 10 raised to minus 8 joule per meter square per second per Kelvin to the power 4. So this power radiated by this body, and this law is basically related to perfectly black body. Power radiated by perfectly black body is directly proportional to fourth power of temperature. So if temperature is more, it will radiate more power. Okay, that is the meaning of this. If temperature of the body is more, it will radiate more power. That was simple as this. Same law they have applied further for ordinary body also, that we will see. Now let's see. So we know the radiant power is nothing but the R. We have represent radiant power by R, but we know radiant power means what? Amount of heat radiation radiated per unit area per unit time. So we can write here Q divided by A into T. This is nothing but a value of R. Amount of heat radiation radiated RQ per unit area per unit time, that is nothing but R, and equal to what? That we can write here this as sigma into T to the power 4. Why so? Because R equal to Q divided by A into T. This already we have learned in the definition of radiant power. Okay, so we get this. So R Q divided by T equal to sigma T to the power 4. This is the equation for black body. If we want to apply the same equation for ordinary body, this one, this all things are for black body we have applied. So this is black body, we can apply this equation. Suppose I want to apply ordinary body. Ordinary body, what are the changes? What do you think? So we should write here R equal to, what should we change? There might be change in coefficient of emission or emissivity, E into sigma into T to the power 4. E for perfectly black body it is 1. So you write it or don't write it, doesn't matter. But ordinary body, it has value of E always less than 1. So E into sigma T to the power 4. This is the same law, Stefan-Boltzmann's law for ordinary body. Just remember, here we have not taken an E because it is E equal to 1. Everything absorbed, everything get emitted by the black body. But here it is not black body, so it has some coefficient of emission, so that is nothing but E less than 1. That's why we should consider E here. That is the only difference. Apart from this, suppose we have the hot body. Suppose hot body we have taken, hot body whose temperature is suppose T, and this hot body was kept in a cooler surrounding. This hot body is kept in a surrounding whose temperature is less than the hot body temperature T0, such that T0 less than T. So this become hot, this become cooler surrounding. So this is nothing but a surrounding temperature T0 is less than the hot body temperature. When hot body is kept in a cooler surrounding, how much energy radiated by the body per unit area per unit time, that we have to find out. So we'll write that energy here. Energy radiated by the, when hot body is kept in a cooler surrounding, how much energy is radiated? So that we have to write. So energy radiated per unit area, per unit time, that we want to find, and that is equal to what? Sigma into T to the power 4. That's much simple it is. And this is for perfectly black body. What about ordinary body? It would be what? Okay, or only E would become here, that's it. So this much energy is radiated by the hot body when it is kept in cooler surrounding. Opposite to this, how much energy hot body absorb? This radiated means emitted by the black body. Now how much energy when hot body is kept in cooler surrounding, it will radiate the energy, that we have written by this equation. But at the same time it radiate as well as absorb. So how much energy it will absorb when it was kept in cooler surrounding? That is nothing but what? Sigma into T0 to the power 4. That much energy is absorbed. This is radiated, emitted. Energy absorbed when kept in surrounding, cooler surrounding, is sigma T0 to the power 4. This is radiated, this is absorbed. So what is net loss of energy? So net loss of energy can be found out from this. So we can write this: net loss of energy when hot body is kept in a cooler surrounding is equal to what? Sigma T to the power 4 minus sigma T0 to the power 4. Sigma is common, T to the power 4 minus T0 to the power 4. This much energy is nothing but a energy lost in the surrounding. Loss of energy in the surrounding, sigma T to the power 4 minus T0 to the power 4. Loss of energy to surrounding by perfectly black body. Apart from this, same loss we want to find out for ordinary body. What should be that? Same thing it is. Only what? Sigma into E into T to the power 4 minus T0 to the power 4. So this is the equation for net loss of energy by ordinary body. This is equation for black body, net loss of energy by the perfectly black body. That is the only difference. Apart from this, here we assume that hot body is kept in cooler surrounding. If opposite thing was done, cooler body is kept in hot surrounding, okay, in that case what should be the loss? T0 comes earlier. Sigma T0 to the power 4 minus T to the power 4 for perfectly black body. Ordinary body, again sigma E T0 to the power 4 minus T to the power 4. That is the only difference. Apart from this, here at the last, just last paragraph they have taken. In that paragraph, what they have mentioned, if absolute temperature of body is double, means we have increased the temperature of hot body by double temperature, double. The power radiated increases by the factor 2 to the power 4. Power radiated increases by 2 to the power 4. It is 16 times get radiated increases. Why so? Because if we increase the temperature double, so it is 2. Initially it is 1, now it is 2. 2 to the power 4, 16 times there would be change here. So that is the point to be remembered. If absolute temperature of body is double, power radiated increases 16 times, because as itself law says, it is directly proportional to 4th power of temperature. So I hope you got this topic. In this fashion we have completed this chapter also. In next period we will start the next chapter. So watch my video, and while after watching, try to understand the same topic by reading the book on the same page. So still, if you have any problem, you can free to ask me on my number. You know my number also. But here remember, don't jump directly to the next and next video. Go serially, one by one go. Then and only then you get through knowledge of this. Thank you.